Right. Very good evening, everyone. I welcome you all to ACE Engineering Academy, ACE online platform. Yesterday, we have discussed about the preparation strategy of communication systems, especially for GATE and ESA examination. So, today as a continuation session, the second session, I will be discussing about important concepts that you need to stress on this particular subject. Myself, C. Saravan Kumar, IES 2011 batch and MTech from IIT Delhi in Optoelectronics and Optical Communication. I have been engaged with classes in ACE Engineering Academy from last 10 years. I take here communication systems, signals and network theory for EC, electrical and instrumentation branches. Right. So, I will just start my discussion like this. Yesterday, those who have seen my video, the preparation strategy, I have asked one question in that. I asked why if you list out the FM radio stations, I will just put the question because some new people might be seeing now. The question that I have kept here is, if you see FM radio frequencies, just little list out 2, 3, let us assume 91.3, 93.5, 98.7 and so on. So, if you just look into your mobile and see that FM radio, it is already in the band of 88 to 108 megahertz. This is the band allotted to FM radio. And if you see the channels, if you go for auto tune options, most of the channels listed out by your mobile will have this dot after dot, the number that you are getting is an odd value. This is mostly odd. I asked the reason for this. It's a very good technical question. What is the reason for this number after the dot happening to be an odd value? So, I will start my discussion with this straight away, this topic. This comes under our analog communication frequency modulation schemes. So, why this is happening here? I did not get any answer. Yesterday some were telling that FM operating frequency is 88 to 108 megahertz, but no one has replied a correct reply for this question. So, let me tell out the reply for that. It is a very good interview question also. So, basically what are the standard specifications you are following? The maximum frequency of message signal in FM radio, we take it as 15 kilohertz, and the maximum frequency deviation, we take it as 75 kilohertz. So, these are standard specifications. So, obviously the value of beta modulation index in case of FM, delta F max by F max comes out to be 5. Is it correct or not? 75 by 15. Now, if these are the specifications, what is the bandwidth allotted by Carson's approximation? This is how you have to learn the subject. All these are formulas of your wideband FM signal. Instead of touching all the topics and listing you the formulas, I am trying to tell you the concept so that you can automatically get in grip with those points. So, what is the bandwidth using Carson's approximation? It is 2 into delta F max, or you can straight away write this as 2 into beta plus 1 into F max. Is it correct or not? Now, whenever you have more than one channel getting transmitted or more than one station transmitted on a same channel, we use some free band between two set of frequencies, that we call it as guard band. So, some band allotted which is generally a guard band. So, this is a bandwidth per station. So, if you specify these parameters here, you will get a 2 into value of beta is 5 plus 1 into F max. Value of F max which you are having is 15 kilohertz, added with a guard band generally taken as 20 kilohertz. So, what happens to this value? 12 into 15, so you will get 180 kilohertz here, added with 20 kilohertz. So, what is the bandwidth per channel you are getting? Therefore, bandwidth per channel is equal to 200 kilohertz. Done. Now, this is not answer to my question. What I have explained to you is what is the bandwidth that you are allotting per channel. Okay. Now, because this bandwidth is 200 kilohertz, what actually happens in the system? You will have more than one station in the total allotted bandwidth or not? So, what you are doing, we are doing a transmission of each channel. So, suppose if I take the first station, what is the carrier frequency of the first station? The bandwidth allotted is 200 kilohertz. That means, if you start with 88 megahertz, because this is the starting point of your frequency, it should stop at 88.2 megahertz or not? 200 kilohertz bandwidth, na? 0.2 megahertz means 200 kilohertz only. So, what is the center frequency? This is what we refer to as a tuned station frequency. We call it as Fs, generally denoted as Fs. So, what will happen to the next station? Obviously, it will be 88.3 because it will have its own upper sideband and lower sideband. Next station 88.5. So, what is happening? Whenever you take that center frequency as tuned station frequency, obviously the carrier frequencies which you are considering will have an odd value after the dot. So, this is the first station. Second station, automatically it becomes 88.3 and so on, 93.5, 98.7, all your favorite channels, if you check, it will be like that. At the same time, there will be certain stations where there will be an even number after the dot, like 101.6, 102.4, some stations are there. If you closely observe, again these even stations, most of the stations are with Government of India. They are not sold to the private people. They are mostly, I am not telling 100%, 80% of such stations are with the Government of India. So, they intentionally did this because they need to keep some stations with them itself without selling them. So, this is how the actual concept of that value after the dot came to be an odd. So, it is a very good technical reason, you know. These type of questions generally when you go for good organizations like ISRO, DRDO, even ESC interviews after you selected for the mains exam, they ask these model of questions. So, it is like, you know, application based. When you see an application, how well you are connecting with your learned concepts. So, you can see here all these formulas we use for calculating the bandwidth or not. So, once you connect this with an application, the way of understanding the subject also becomes interesting. So, this is how try to learn each and every application. So, with this I have told you one concept of FM radio or FM modulation schemes, which is one of a very important concept of our analog communication systems, right. So, this is one first question that I have taken in this very session. So, important concepts when you keep touching, there is lot to explain. So, what I feel is, let me take a question, explain the background of that question and then tell how to understand the question and answer that question. And these questions are not any of the questions given in the previous exams as of now, and not normal standard questions, little bit different models. I will not take more, maximum 3 or 4 questions, that is it. And you will try to understand the subject by reading these questions, okay. Let us go into that discussion. Right, let us see this question. This is question number 2 of the day, okay. Consider a baseband signal. Now, understand the terminology. Each and every point is very, very important. Consider a baseband signal. Baseband signal means generally the meaning is message signal. Band limited signal, message signal, baseband signal, modulating signal, all these comes under the category of low frequency signals, okay. X of t, so he is representing it as x of t, modeled as sample function of zero mean Gaussian process having variance of sigma square fx. So, this is how the questions will actually come in your exams, in GATE particularly. So, what is he telling here? How differently he framed the question, you observe carefully. He did not take a deterministic signal here, he took a random process. So, x of t is representing a random process. Anything can be given as a message signal. There is no need that it should be only deterministic signal. Now, the signal that is given is a random, first he considered as a random process. In this random process, he is considering x as random variable. Now, what is the nature of the random variable? The nature of the random variable is Gaussian random variable. And what are the properties of this Gaussian random variable? It is having a mean value, means expectation of a random variable is 0, and it is having variance, means what? Sigma square x. Now, this is equal to variance. You very well know variance is always mean square value minus mean whole square. So, because mean value of this random variable is 0, obviously its mean square value also will be equal to sigma square x. Finish. So, these are all the points that you need to understand. Okay. Now, if you sketch this, how does this look like? So, what is this now? I am considering my x-axis as random variable x. What type of random variable? It's a continuous random variable. Done. And what is the nature of this random variable? It's a Gaussian random variable with mean 0. So, how will you represent a Gaussian random variable? You will have a bell-shaped curve like this. Always Gaussian random variables are centered about the mean. That means the value of mean is 0. Center point is 0. And this y-axis represents probability density function of this random variable, which we write it as f of x. So, this much of data is there in this first 3 lines, that is all. Now, you may ask me, sir, from where you are getting these questions, why you are telling all this? These are all standard questions taken from standard very good textbooks. John D. Prokis is one of a very good textbook for digital communications, and these questions sometimes are listed in standard websites also, like you have NPTEL program of IITs. There also some questions are there on these models. They are not given for solutions, they are given as a questions for practice, or sometimes these lecturers and professors programs will be there, where they have to enroll and complete the courses from college point of view. In such examinations, these tests are also given. So, you know, examiner don't generate new things, that possibility does not arise. He will keep on tracking with different models of questions coming from standard books. It may not be the same question as it is, but model remains same. So, this is how you can model a question extraordinarily. It is not a straightforward question. See how he has given. So, what is he telling finally? I have taken a random process, I have taken a random variable, it has a mean value, it has a mean square value, and it has a variance. Now, this probability density function tells about the properties of your message signal. So, is it a random signal or not? So, instead of giving a single tone signal like am cos 2 pi fmt, which we generally discuss every time, he has given a random signal with these properties, and this represents the probability density function of that random variable. So, this much of information is there in this particular question. Now, continue. What he is saying? It is given as an input to quantizer. Now, what is a quantizer? In our syllabus, we have only one type of quantizer, uniform quantizer, and that too a mid-rise quantizer. So, that he need not explicitly tell it, because anyhow everyone knows only uniform quantizers are there in GATE syllabus. We discussed 2 types of quantizers there, mid-rise and mid-thread. But generally by default, when nothing is given, we go for mid-rise quantizer, right, with maximum levels set at plus or minus 4 sigma. That means what is the meaning? He is not giving this entire random variable message signal to the quantizer. He is giving only when the levels are between plus or minus 4 sigma x. That means what is the meaning? What he is telling here, he is marking a minus 4 sigma x somewhere here and plus 4 sigma x somewhere here. Only these values are given as an input to the quantizer. only these values. That means indirectly he is saying your V max, which we standardize at 4 sigma x, and V minimum is at minus 4 sigma x. Only these are given to quantizer. Only these are given to quantizer. Clear? Understood my point or not? Understanding question is a very good art. Once you understand, you will go in the correct direction. You will not make mistakes. Now, if the output of uniform quantizer is coded with n bit sequence, so what is this modulation scheme is using here? Obviously PCM, and it is coded with n bit PCM system. That means whatever the quantizer takes, the voltage levels are between this and this with maximum and minimum values, and once these values are quantized, the output of the quantizer is encoded with n bit sequence, normal n bit PCM system. Determine the signal to quantization noise ratio at the output of the quantizer. So basically he is asking what is the value of signal to quantization noise ratio. Finish, that's all, that is the question. Do you get my point or not? Now what is signal power, tell me? It is a random signal or not? So what is the power of a random signal? Its mean square value. Mean square value of the random variable is signal power. So what is the mean square value of the random variable? Sigma square x over. That's it. This is power, na? So I am writing unit as watts. Now what is quantization noise power? For all uniform quantizers, quantization noise power is del square by 12. Correct or not? Quantization noise power is always equal to del square by 12. For all uniform quantizers, mid-rise quantizer, this is fixed. It will not change. Now what is delta? Delta is a step size, which is fixed for a given quantizer. So what is this value of delta? V max minus V minimum by 2 power n. Standard formulas. That's what I told. If I touch one question, all the points related with PCM will come here. See how beautifully all the points are coming. This is how you can easily understand the concept also. Don't read theory much. Theory is waste of time. Understand concept and then apply with problems. Even if you don't understand the concept well, once you do numericals, automatically everything will be cleared. So try to spend more time on problems rather than reading theory in any textbook. Up to a certain extent it is fine, but don't read too much and waste your time. This is how you can understand. Now what is V max minus V minimum? Is it 8 into delta x or 8 into sigma x or not? Because he has given range is plus or minus 4 sigma x by 2 power n. So what is this quantization noise power? 64 sigma square x divided by 12 into 2 power 2n. Correct or not? Del square by 12, na? Delta you got 64 sigma square x by 2 power 2n will be del square by 12. Now therefore what is the signal to quantization noise ratio of this PCM system? Sigma square by 64 sigma square into this value. That means you will get a sigma square x divided by, denominator you will have sigma square x into 64, and in numerator you will get a this 12 into 2 power 2n. So this sigma square x values will get cancelled out, and you will have 4 table. If you take it will be 3 divided by 16 into 2 power 2. Yeah, finish. That's it, over. Is it clear or not? So this is how you can get the reply. Now in exams what they can do? Yeah, they need not give the same question as it is. Na? What they can do? They will tell n as some 3 bit or 4 bit. So up to here the question will be same. Determine the signal to quantization noise ratio at the output of the quantizer considering the value of n to be 4 over in dB. So what will happen? 2 power 2 into 4 means it becomes 2 power 8, 256 divided by 16 into 3, convert into dB and write your answer, fill in the blank. Excellent 2 marks question. So this is how the questions will be framed in your gate like exams. But other competitive exams, time bounded exams, means 1 minute or less than a minute for a question, they cannot ask these type of things. You cannot think. There it is only formula based. So whatever the formulas we are using, standard formulas, just substitute to get the answer. Here also you are doing the same thing, but what is the extra that you are doing? You have to understand this concept and then apply in the formulas, you will get the answer. Usage of formulas is the same. So just knowing the formula, maybe it is sufficient for normal competitive exams. But if you want to clear exams like GATE, then definitely subject is must. This you keep in your formula, you will get your answer, right? So I hope you got a little bit emphasis on this particular PCM model question. So this comes under your baseband data transmission syllabus. Yesterday I have clearly explained the syllabus. If you did not watch my video yesterday, please go through that. Yesterday I have given the preparation strategy keeping in mind especially GATE examination. So all the syllabus also I have clearly mentioned there and how to prepare and how much is the weightage that you can get from each topic. So as per that only I am taking some questions randomly and trying to explain you the concept that is present in the question. Done? Shall I go for the next one? Right. I will go for the next one. Before going to the next question, this is a bandwidth table, or I can say bandwidth formulas. It's for your reference. For baseband data transmission cases. Okay, so this is a formula which you can use for baseband data transmission cases. So it all depends on the signaling scheme. Keep this point in mind, don't make a mistake. You will have a number of blocks in the PCM system, right? Now, after getting the bit rate, so when we take a bit rate of the PCM system is n into fs in bits per second. So this bit rate will be decided after you do encoding. N bit PCM will be there na. After performing that encoding operation, then we will decide the bit rate. Up to this stage, no tension at all. Once you decide this bit rate, you have to do the transmission of your data. Baseband data transmission means what you will do, you will transmit on a channel. Physical channel will be there, like an optical fiber cable or a coaxial cable or a twisted pair cable. Such a cable will be there. So when you want to transmit the data, obviously you have to have a representation of a binary data. Some electrical format representation is there. So that is what we refer to as electrical representation of binary data, line coding techniques. Now, this line coding schemes or techniques that you use here will decide the bandwidth. It is not the bit rate of the PCM system that is bandwidth. Most of the time students make this mistake. RB and bandwidth, they think it is same. No. RB is bit rate, the rate at which your PCM is generating the binary data. Unit is bits per second. Bandwidth, the minimum space required for your signal to go in a channel. Its unit will be in hertz. Okay. Now that completely depends on your line coding scheme. So what do you mean by line coding scheme? Electrical representation or physical representation of your binary data. Sometimes you may represent it with rectangular pulses, sometimes you may represent it with raised to cosine pulses or with Nyquist sampling pulses, depending on the availability of your source, you will do this line coding scheme. So based on this line coding scheme only, bandwidth will be decided. Okay. Now, what are the different line coding schemes we are having? These are all the line coding schemes. That is what we generally call it as signaling schemes. I am not explaining what is each signaling scheme because it itself is 2-3 hours class. Normally in my class I first explain that part and then decide the bandwidth, because every line coding scheme has its own power spectral or energy spectral density. So if you watch that energy spectral density, you need not derive it. If you just visualize it, then you will understand the concept of bandwidth very clearly. That is what practically I tell to my students. Now, I am unable, I cannot tell all that because this is only a session where we have to touch all the concepts to the maximum extent possible. So that is the reason I have given this table. So if you take these different signaling schemes, on off, again you have RZ and NRZ, two techniques. The bandwidth required is equal to RB. If it is on off, unipolar, on off or unipolar both are same, RZ technique 2RB. If it is polar, RB. Polar RZ 2RB. Whether it is bipolar RZ or NRZ, it is RB. Now, most of the times, if nothing is specified, then bandwidth is considered by taking a bipolar coding scheme. Rectangular pulses, whenever you do transmission, we by default consider coding scheme used is a bipolar coding scheme. This is also called as AMI, alternate mark inversion. So if you use this coding scheme, then what is happening to your bandwidth? Your bandwidth and bitrate are same, which becomes RB, now unit will be hertz. So this is a case when you use this alternate mark inversion or a bipolar coding scheme. So many of the times you might see in standard textbook saying bitrate and bandwidth will be same, and they simply write RB bits per second as bitrate and RB in hertz for bandwidth. But be very careful, they are not same. They will be same when you are using this coding technique. Now if you go for higher order schemes like Manchester, where each bit is represented with two different voltages, then bandwidth will get doubled. Bandwidth will increase tremendously. Now I explained yesterday, bandwidth is like money. You have to get your work done by spending as less money as possible. So increasing bandwidth is not that a good idea up to certain extent. So that's the reason generally we fix most of the times to bipolar NRZ coding schemes. Done? Now the problem with this rectangular pulses is, if you do your transmission using a rectangular pulse, what happens is we have a problem of pulse spreading, which we call it as inter-symbol interference. That means I'll explain you in a very simple language. Just focus on this. That will tell you why we are considering these raised cosine pulses and Nyquist sampling pulses. Most of the students, they will not even study what are these. They will just know this name. Immediately they will know these formulas. In interviews they will ask why you are doing this. That is correct thing, at least you should know the minimum idea. So the problem here what you face is, just understand my point. I will explain you in a simple language. I have rectangular pulse transmission. So let me assume I am doing a transmission of data using a rectangular pulse, because all those are rectangular pulses only, all coding schemes, rectangular coding schemes. So this is a pulse in time domain. Let us assume for 1 bit duration. So minus TB by 2 to plus TB by 2. Let us assume the amplitude is 1. This is a pulse that I am using for representing, let us assume, binary bit 1. So how will you decide the bandwidth? You will decide the bandwidth by taking its energy spectral density. So what is the energy spectral density for a rectangular pulse? It will be a square function. Correct or not? Rectangular function transformation is sinc function. So when you take Fourier transformation square, it gives you energy spectral density. So that means what would be this shape you will have here? You will have major lobe centered about the origin, and all remaining will be minor lobes. not that good at drawing the pictures, but concept you have to be very, very clear. This is how it looks like. Done? So this x-axis is now f. Is it clear or not? So this is your f equal to 0, and this represents your energy spectral density of pulse p of t. Okay. So when you take p of t, what is its Fourier transform? It is p of f. What is p of f? It will be sinc function in frequency domain. Coefficient of f is total width, so it becomes TB. These are some shortcuts which I tell to my students to easily remember. Rectangular function transformations are always sinc. First write sinc f because you are writing in frequency domain. Now coefficient of f is total width of the signal, which is TB. Coefficient of sinc function is total area. What is the area? Rectangle, base into height, TB into 1. So this coefficient will be TB, finish. Now if you take energy spectral density, here the meaning is you are taking mod of this P of f whole square. So that means this function is like a TB square, sinc square, TB into f. Okay. Now where is this function becoming 0? That means what? You are equating this sinc square TB f to 0. I wanted to know the 0 crossing points. That means what you are doing? You are taking pi TB f, equating it with plus or minus n pi. So the value of f will be equal to plus or minus n by TB. So this value will be 1 by TB, this value will be minus 1 by TB, and so on. Correct or not? Now if you want to tell the bandwidth, what is the ideal bandwidth? It tends to infinite because your pulse is not stopping, it is going up to infinite. So ideal bandwidth is infinite. So what you are doing to limit the bandwidth? We take the pulse only in the duration of this major lobe. Is it correct or not? This indicates your major lobe. Major lobe always constitutes 98% of total signal energy. So what you are doing? You are restricting your spectrum only to major lobe. That means the practical bandwidth when you fix is equal to, when you restrict your pulse to this major lobe, is it looking like a band limited or baseband signal or not? Whose maximum frequency is 1 by TB. So practical bandwidth becomes 1 by TB, or simply 1 by TB is nothing but bit rate RB in hertz. Then that is how you got this formula of RB. That is how you have to understand the subject. Then it will be crystal clear for you. Okay, understood? So I have proved that result. Now come back to the original story. Why I told all these points? To explain you the concept of sinc and cosine functions. RCP, raised cosine pulses. Now everything is beautiful here. You have limited your signal, so bandwidth has been limited. But what is the problem? Think in a simple way. Have you stopped your frequency domain function to that major lobe or not? That means what you are actually doing here, we are not taking the entire function. What you are doing? You are restricting your frequency domain function only to its major lobe. Correct or not? So you are taking something like this. You use a low pass filter and filter out your spectrum only to this part. That means no longer this is your P of f or energy spectral density of that particular function. This has completely changed. Frequency domain function is changed. Which part of the function is changed? X-axis is f. I have restricted only to major lobe from minus 1 by TB to plus 1 by TB. Correct or not? Now when you restrict your function to a particular high frequency, means what I am doing, I am passing all my low frequencies, but whenever these high frequency components are coming, they are all getting stopped because we are restricting ourselves to 1 by Tb. Now, because your frequency domain function has changed, automatically your time domain function also will change or not? It should change. Logically that is correct. If this is my function in time, this part of the frequency is entire spectrum up to infinite, but you are not doing that, na? You are stopping it here. So what will happen in time domain? Here also it will get changed. So how it is going to get changed? Some part of the function will remain constant, it will be having constant amplitude, but then it slowly gets extended. So this is what we call it as pulse spreading effect. So what is the problem with this pulse spreading? It will not stay in its house, it will go into next house. That means what will happen? It will get extended to the next pulse. So your next pulse might be something like this, and then it will also have some constant, and then again it will deteriorate. Did you understand my point or not? So what is happening here? The pulses are getting overlapped with each other. So because of this change in the pulse or spreading of the pulse, there is interference of one pulse with its next pulse or its previous pulse. So what will happen? Because of this interference, the probability of error will increase. So this interference is what we are calling as intersymbol interference, denoted as ISI. So because of this ISI, what is the problem? Probability of error will increase. In interviews, they will only ask what is ISI. I have seen many students telling ISI is a noise. Be very, very careful. ISI is not a noise. Noise is something that comes as a part of your channel. Once you transmit your signal onto a channel, but here it is coming because you have band limited your signal in frequency domain. It's a process that is coming into the picture. And this spreading happens at the edges, because high frequency components in frequency domain generally denote sudden changes in amplitudes in time domain. So whenever these sudden changes are occurring, then your pulse spreading will take place. Because of this, ISI comes into the system. And what is the problem with ISI? It increases the probability of error. Understood? Now, somehow you have to rectify it, because this pulse spreading is too high, then obviously 0 will become 1 and 1 will become 0. Your entire process of digital communication gets lost. So what we have to do, some way or the other you have to limit this. So what they have done is reversed the story. Means what? They brought this into time domain and they took this into frequency domain. So instead of limiting your spectrum in frequency domain, what this entire problem, why it came? Because you stopped the signal at 1 by Tb or not? You don't stop, let it automatically stop. That means what? You take rectangular pulse in frequency domain. Automatically it is stopped or not? You did not stop it by using any low pass filter. This pulse we took in frequency domain and automatically this pulse came into time domain. And the advantage what you will have, because you sample only at 0 or integer values of Tb, you see here what is happening, you will get pulse only at this value. All the remaining values, amplitudes are 0 automatically. That means if you want to do your transmission without any ISI, then what is the only way? You have to do transmission using sync pulses. So these Nyquist sync pulses are used for 0 ISI. So if you understand the subject, you know, then it becomes clear. For what purpose these pulses are used, you should know. So what is the advantage of using ISI? Automatically you are getting two advantages. What is the first advantage? ISI is becoming 0. Means your probability of error is minimized. Don't think probability of error is 0. There is no chance. Probability of error will be minimized. Then what is the second use you are having? See the bandwidth. Is it becoming minimized or not? If you take any of the other cases, the bandwidth required is more than RB by 2. Correct or not? This is generally the pulse that we use. If it is rectangular pulses, you will get RB. If you use Nyquist sampling pulses, we are in a position to remove ISI completely from the system, making the probability of error minimized, and also we are minimizing the value of bandwidth. So because of these two advantages, we try or we prefer transmission using Nyquist sampling pulses, right? Now what about raised cosine pulses, why they came into picture? Now everything is excellent, you are telling use ISI, but is it possible to generate these Nyquist sampling pulses? Generation is okay, but the problem is timing errors will occur. In digital communications, major problems comes with timing error. Means what? When you want to sample a function at say some 0 seconds, your system will sample at 0.2 or 0.3 seconds. So that small interval of 0.2, 0.3 is enough to increase the probability of error. So to compensate those timing errors, we used raised cosine pulses. Nothing is there. Raised cosine pulses means you want to sample at 0. Just see this, you will understand. You want to sample at 0. If your circuit is extraordinary, it will sample at 0. But nowhere it is possible. Some small errors will come up. So instead of sampling at 0 seconds, let us assume this value is 1. I am sampling at 0.2 seconds. So what will happen? If you sample at 0 and give it to your receiver, it will operate perfectly and generates a probability of error. If you sample at 0.2, this value which you are getting here might be some, let us assume 0.8. So it will sample this value of 0.8 and give it to the receiver. Your receiver will again generate a probability of error, but that value will be little more than the previous value. So what is your target? You cannot sample exactly at 0, that is true, you have to accept. But can you increase this value from 0.8 to very much close to 1? Let us assume some 0.9 is there. So what is happening? You are not able to generate that minimum probability of error. At the same time, it is not becoming very high. You are keeping somewhere in between this minimum value and the other value, so that the operation or performance of the system is good. So for that purpose, what you have to do? You have to make this 0.8 to be 0.9. Let us assume like that. So what you will do? You have to pull this pulse a little bit above or not. That means what you are doing? You are narrowing this pulse and then pulling up. Did you understand or not? You narrow this pulse, means this width is there, narrow. Automatically pull it up. So when you do this narrow operation, it is getting pulled up. That is what is called as raised cosine pulse. That is the reason why that name is given, raised, pulling up. So that this amplitude of 0.9 can become 0.8 can become 0.9, resulting in lesser probability of error. And even though timing problems are there, the probability of error will increase a little bit, but it does not affect the overall performance of the system. So when you use this raised cosine pulses, this is the bandwidth. So normally it is RB by 2 with Nyquist sampling pulses. Here this value becomes RB by 2 into 1 plus alpha. What is this alpha? It is called as roll-off factor. That's all. So this roll-off factor values are always between 0 and 1. If you take 0, then it will be RB by 2, means roll-off factor 0 means what? There is no pulling of the pulse at all. Raised cosine pulse and Nyquist pulse both are same. If you pull it, maximum how much pull you can do? Alpha is 1. That means maximum timing errors are there. You take alpha 1. Minimum timing errors are there. You take very close to 0. Based on that, your bandwidth will increase. So what is the bandwidth? It will be somewhere between RB by 2 to RB by 2 into 1 plus alpha. So that extra bandwidth will be used for timing errors problem. So that is how we are getting this value. Done? Now, see the last one. If you go for higher order modulation schemes, now what is the meaning of higher order modulation schemes first of all? whatever the data that you are doing a transmission is generally 1 bit per 1 sample. That means what? Your carrier or whatever the representation that you are doing, it represents either bit 1 or bit 0, that's all. That is normal transmission in bits per second. If you do more than 1 bit per transmission, that means what? You take 4 bits as a symbol. That means instead of transmitting in bits per second, you are now doing transmission of symbols per second. The rate at which your symbols are getting transmitted is called as baud rate. Okay, I am introducing those terms also here. All these things are interlinked with each other. Bits per second is bit rate, symbols per second is baud rate. So if you are able to transmit 4 bits at a time in place of 1 bits at a time, how much is the bandwidth you saved? Is it 4 times the bandwidth that you have saved or not? That concept is nothing but higher order modulation schemes. So depending on the number of symbols you have in your system, you can decide the bandwidth. So what would be the bandwidth? You take the normal bandwidth, whatever the pulse you used. Suppose you used bipolar pulses, bandwidth is RB. If you have used Nyquist pulses, RB by 2, substitute in numerator, divided by number of symbols that you are transmitting, 4 symbols or 16 symbols or whatever that symbols you are doing, log that symbols to the base 2. That means how many bits are there per symbol, that will be represented in the denominator. So this value will be your bandwidth. It will definitely decrease if you go for higher order modulation schemes. So this is how you are having formulas for all baseband data transmission techniques. So I have discussed just the formula with all these points. So we got a problem related with baseband data transmission, a very good question which tells about the signal to quantization noise ratio of a PCM system, and formulas related with all the bandwidths for baseband data transmission, different type of pulses. And I have touched the concept of ISI also, very, very important. You can expect a 2 marks question next year. So why that ISI is coming, what is ISI, and how to mitigate ISI, means how to reduce it, either by using Nyquist sampling pulses or by using raised cosine pulses. So which factor is getting affected? Bandwidth. So all these points I try to explain with this table. So if you have a connection of subject in this fashion, then automatically it becomes easier for you to remember. You need not memorize anything. Automatically your brain will get tuned up. Hope it is clear. Okay, I am not trying to confuse you. I am trying to explain concept clearly. Even if it is 1 question or 2 questions, it does not matter. The way how you are building your concept is very, very important. Right. Let me take one more question. I think I don't have much time. Maybe 15 minutes is left over. So let me take one more question. See this question. It's also an excellent question. Consider 216 Qualm. This is a question related with constellation plot. By this time you might have seen this represents a constellation plot. Where you will get constellation plots, it comes in your band pass data transmission. So basically I explained FM, 1 question from analog communications, baseband data transmission, 1 question related with PCM, bandwidth requirements, and 1 question, last one, from band pass data transmission. Okay, I am giving you the question clearly. See this. Consider 216 Qualm. Qualm means what? Quadrature amplitude modulation or quadrature amplitude multiplexing. 16 Qualm means what? The value of m which you are considering here is 16 and the value of n automatically becomes 4. That means you are clubbing 4 bits at a time and transmitting it using 1 carrier. That is what is called as m array transmission. Which model of modulation scheme you are using? M Qualm you are using. So quadrature amplitude modulation will have variation in signal as well as phase. So some bits you might use for representing amplitude and some bits you might use for representing phase. If you take the first 16 Qualm plot, is it a circular plot or not? First concentrate on what I am telling, then you read the question. I am taking 16 Qualm, I am representing 2 circles. That means what would have been happened out of this n equal to 4 bits, in circular Qualm, I used 1 bit for representing amplitude. So 1 bit is representing for amplitude means how many different amplitudes are there? 2 amplitudes, because 1 bit will give you 2 representations. Those 2 are nothing but your circle radiuses. First circle radius R1, second circle radius R2. Okay, and how many bits are remaining? 3 bits are there. These 3 bits I have used for phase changes. That means each circle should have how many phases? 8 phases. That is the reason having 8 black dots on the inner circle, 8 black dots on the outer circle. Got my point? Now, what is the phase difference between each of these points? It is 2 pi divided by that 2 cube, which is 8. Means the phase difference between individual points will be 45 degrees over. Now, all these points are related with 16 Qualm with circular constellation plot. Okay, now come here. Next part is 16 Qualm rectangular constellation plot. Now, how you have here, you can see very clearly, I am using a amplitudes on x-axis as well as amplitudes on y-axis or not? Is it correct or not? So what I am doing, I am using 2 bits for representing amplitude and 2 bits for representing phase. So here n equal to 2 for amplitudes, 2 bits are used for amplitudes means you will get 4 different amplitudes. What are those 4 amplitudes? A, minus A, 3A, minus 3A. Similarly on y-axis. So I got 4 different amplitudes. And how many bits I am using for phase? 2 bits I am using for base. Finish. So this is how you got a 16 Qualm, which is now representing a rectangular constellation plot. So whenever you have Qualm, it will have 2 circles, 2 rectangles in this fashion only. The same if it is 16 PSK, then how it will look like? It will have all the 16 points on a single circle. That is how you can distinguish between 16 PSK and 16 Qualm. Right. This is one set of point. Now, what I am asking here, see the data, data is not yet completed. The minimum distance between the neighboring points of circular Qualm, that is distance between A and B or distance between A and D. That means what is the meaning here? If you take the distance, either the distance between this A and B, this one, or the distance between this A and D, this one. The distance between these 2 points is equal. This is what we refer to as a D minimum. That is what is the data given to you. So the minimum distance between the points A and B or A and D is P. That means D minimum between AB or D minimum between A and D is P. And similarly, the minimum distance between the neighboring points of rectangular constellation plot means this one is 2A. Then this is a data given to you. Okay. What is he asking? Actually 3 bits are there. I thought of explaining only 1 bit. Let me take the first bit. Determine P in terms of A. That means what is the comparison you are doing? You are comparing the D minimum of a 16 Qualm with a circular constellation plot with D minimum of a 16 Qualm with a rectangular constellation plot. That means we have to check whether this P is equal to or whether this P is less than 2A or whether this P is greater than 2A. Correct or not? What is the advantage of doing this? First of all, when you do this, what will happen? You will be in a position to tell which would be a better constellation plot, because the probability of errors depends on D minimum. That is the logic here. So what is the concept here? If the value of D minimum for a given constellation plot is more, then the probability of error will be less. That's all. That is the whole underlying concept. So if P and 2A are same, you use any plot, there is no change. If P is less than 2a means what? The D minimum in first plot, circular plot, is less than the D minimum in rectangular plot. You prefer transmission using rectangular plot. Obviously, the probability of error which you get will be less. If P is greater than 2a means what? The D minimum in the circular constellation plot comes out to be greater than rectangular constellation plot. You prefer transmission using circular plot because it will generate a lesser probability of error. Got the concept? So, this is how you can do comparison of different constellation plots using concept of D minimum. Okay. Now, read the question fully, you will get an idea. Determine P in terms of A if condition is there. Total energies E1 and E2 taken by both the constellation plots is same. That means what? Energy taken by circular constellation plot and energy taken by rectangular constellation plot for both the 16 Qualm schemes is same to same. Under this condition, you can compare D minimums. This is one part. Other part is, you only take P equal to 2a. First I have explained. What I have explained? Take E1 and E2 to be same. I will explain the points clearly because time is also running up. Let me come to a conclusion how to solve this question. What I am telling here? I am telling that energy taken by both the plots is same. I only gave you that point. That means it is like, I will tell you one example. See here, two houses are there. Current supply to both the houses is same. I am giving 100 units to the first house, 100 units to the second house. In the first house, only 2 tube lights and 2 fans are running. And in the second house, 4 tube lights and 4 fans are running with the same supply. That means which is an advantage? Is it the first house or the second house? Second house, because whatever the spending of expenditure is there, your output is more in that case. Same logic you apply here. I am supplying both energies to be same. Energy taken by both the plots are equal. And I am calculating the D minimum in first plot and D minimum in second plot. Then definitely they will not be same because the shapes are different. They will never be same. If at all they are same, that means for the given E1 equal to E2, you use any plot, there will be no change in probability of error. Otherwise, for the same energy, if P is less than 2a, then what is happening? For whatever the energy you are using, second constellation plot D minimum is more than the first constellation plot D minimum. That means use second plot so that probability of error is less. Third case, for the same given energy, P is greater than 2a, means D minimum in the first plot is greater than the D minimum in the second plot. Then obviously you prefer using the first plot so that probability of error will be less. This is one case. What is the other case? The other case that we can study here is, I will just tell that case, we can wind up. What I am taking in the second case is, I only give you P equal to 2a. It means what I am telling you, you don't break your head. The minimum distance in first two plots is same. I only told that point. That means obviously whether you do transmission with first plot or second plot, the probability of error remains same because the D minimum in both the cases are same. The probability of error in first constellation plot and the probability of error in the second constellation plot are one and the same. There will be no deviation at all. But what is the point that you have to check? What is the point you have to check now? With the probability of errors to be same in both the plots, which plot is taking less energy? Whether the first plot is taking less energy or the second plot is taking less energy. Definitely they will have different energies. You are only telling that both the energies are, both the D minimums are same. So you have to calculate energy of first one and second one. For the same probability of error or D minimum, which plot takes less energy is an advantage for us. So that is how you can do comparison of two different constellation plots. So I have compared same modulation scheme here, Qualm, 16 Qualm, but shapes are different, rectangular and circular. Now sometimes students come to a conclusion that rectangular plots are better than circular or circular are better than rectangle. Don't make such stories. There is no such rule. It depends on parameters. Simply calculate d minimum, see the plot which has more value of d minimum, that plot will have lesser probability of error. So our target is to always consider a constellation plot where the value of d minimum is maximized. That will automatically give you minimum probability of error. Okay? So with a stipulated time, I can cover these points, but these are very good things which I have covered. If you are very sincere in your preparation, you can understand these points. So try to cover your subject in the way I am teaching. Don't simply memorize it. That will not help you in examinations like GATE. Developing concept is more important than getting your right answers here. So try to focus your concepts in a practical way, then automatically that subject will get built up. Okay? So these are some points that I have discussed in today's preparation. Please watch my video, yesterday's video. It has all the syllabus points and also preparation strategy. Today's video, I touched very important concepts from where you can expect definite questions in GATE. Okay? In the coming days, we will be also focusing on important questions or most possible questions that you can expect in GATE exams, but that we will be covering little afterwards. Okay? So I will end my discussion at this stage. I wish you everyone a very best in your preparation for my communication subject. Thank you. Have a good night.